wanted to work through an example that involves Gauss's law. In this particular example, we're asked to imagine two spheres. One of them is a solid conducting sphere. The other one is a solid insulating sphere. And the two spheres carry an equal quantity of charge. Now, in the conducting sphere, the charge resides on the surface of the sphere. And so the charge is a thin layer on the surface of the sphere. It forms a spherical shell at the surface of the sphere. In the insulating case, the charge is distributed uniformly throughout the volume of the sphere. So it's everywhere throughout the volume of the sphere. And we're asked to compare the electrical field at some location outside the radius of the two spheres, whether the conducting sphere's field is larger with the charge on the surface, or whether the insulating field's larger with the charge spread throughout, or they're the same size fields. And so that's our task, and we're going to do this through Gauss's law. Now, you could solve this problem through Coulomb's law, but it would be a horrible problem to solve through Coulomb's law. To solve this problem through Coulomb's law, you'd have to break up the surface of the conducting sphere and the volume of the insulating sphere into lots of little pieces of charge. You could then apply Coulomb's law for each of those little elements of charge or pieces of charge, and then you could superimpose the fields from all those little pieces of charge, either over the surface or through the volume for the conducting or the insulating sphere. That would be an enormous amount of work for us. You can do it mathematically, but we don't want to do that. Gauss's law is a simple and a straightforward way of solving this problem, of comparing the electrical fields of the charged sphere and the insulating sphere, given their different charge distributions. It takes advantage of the symmetry of this situation. It takes advantage of the fact that we're dealing physically with spheres. We're dealing physically with spherical distributions of charge, and therefore the fields that are produced by the spherical distributions of charge, those fields are going to be spherically symmetric also. And so let's work through this problem. So the key idea is that whether we're thinking about the conducting sphere with the charge uniformly over the surface, or we're thinking about the solid sphere with the charge uniformly throughout the volume, those charge distributions are spherically symmetric. Those charge distributions look the same if you look at the spheres from below or above, from the left or the right, from the front to the back. They are spherically symmetric. That means that the electrical fields that those charged spheres create are going to inherit that spherical symmetry. They're also going to have that spherical symmetry. So if you were to look at the electrical fields of the charged or insulating sphere, those would also look no different below the sphere compared to above the sphere. No different from the left or the right of the sphere. No different from the front or back of the sphere. They would have that spherical symmetry. So the first thing I'm going to do is draw those spherically symmetric electrical fields of either the conducting sphere or the insulating sphere. And so that's what I've drawn here in red. These are the field lines corresponding to the electrical field outside the sphere, whether it's a conducting or a insulating sphere. You see they have this spherical symmetry. The field strength is the same above and below, to the left and right, and front and back of the sphere. I'm trying to picture that, draw that. Now, the charge distributions that are creating this arrangement, this electrical field. In one case, there are a charge that's just located over the surface of the sphere. So this is the conductor, and the charge is in magenta. Whereas for the insulator, that charge is distributed throughout the volume of the sphere, so throughout this entire volume. So green is the insulator. But the end result outside the sphere is still a spherically symmetric electrical field because both of the charge distributions are spherically symmetric. We can take advantage of that spherical symmetry to calculate and compare the electrical fields that are created by the solid distribution of charge in green and the surface distribution of charge in magenta. So I'm gonna place in my sketch, imagine in my sketch a closed Gaussian surface, a closed spherical Gaussian surface, concentric on the sphere, centered on the sphere. And we're going to use that imagined concentric spherical Gaussian surface to solve and compare the electrical fields of the conducting sphere and the insulating sphere. So let me draw that. So here's my Gaussian surface in black. I denoted its radius r, and I've also denoted the charge owned by the conducting sphere on its surface, owned by the insulating sphere throughout its volume as Q. And what we're going to do is apply Gauss's flux law to this spherical surface in which the charge distribution resides. And in that way, we're going to figure out an expression for the electrical field for the conducting or the insulating sphere. So let me write down now Gauss's flux law. So here's Gauss's flux law. The left-hand side is the electrical flux through the closed surface. So it's the net or the total flux through this spherical closed surface in black. And over here on the right-hand side is this constant 4 pi times the Coulomb constant times the charge located inside the closed surface. So it's the charge on the conducting or the insulating sphere, which is inside the closed surface. So in this particular case, the flux, electric flux through the surface, because the electrical field has a constant size over the surface because of the spherical symmetry, because the electrical field is perpendicular to the surface, again related to the spherical symmetry, the electric flux is simply the size of the electrical field everywhere on the surface times the area of the surface. There's the product of those two magnitudes of those two quantities. And so that's going to be equal to 4 pi kq. And we can fill in the area of the surface. It's 4 pi r squared equals 4 pi kq. We can cancel out the factors of 4 pi on the left and right. We can rearrange for the electrical field. And it's simply equal, its magnitude is simply equal to kq over r squared. And so that's our result for the magnitude of the electrical field based on Gauss's law. It looks like the electrical field of a point charge, if you look at it. And that electrical field is the electrical field of the conductor's distribution of charge and the insulator's distribution of charge. If they have the same quantity of charge, then they have the same electrical fields outside of the sphere. So you can't actually distinguish between it being a conducting sphere or an insulating sphere, one that has the charge distributed over the surface, one that has the charge distributed through the volume by the electrical field outside of the insulating or conducting sphere. In fact, you can't distinguish between the solid spherical distribution of charge for the insulator, the spherical shell of distribution of charge for the conductor, and a point charge. If the charge was all located at the very center, the Q was located at the very center, that would have exactly the same electrical field. So the answer to this problem is that outside the sphere, outside the conducting insulating sphere, if the conducting insulating sphere had the same charges, then they have exactly the same electrical fields for this spherically symmetric charge distribution.